I might have to turn my video off. Um, my wife is also doing a video call, so I might have to do that. Um, but I assure you, as long as I'm talking, I'm still here. So we were talking about the other day some intermolecular forces and definitely distinguishing between inter and intramolecular forces. That's a very important thing. Now, we are going to kind of continue that. We've got a couple of top hat questions. We got a not a super long lecture for today, um, but we're going to kind of go through a little bit of some models for what this looks like. And so let me go ahead. I am recording, so that's good. I'm going to switch over to presentation mode, and then I'm going to begin my share. Um, in the event that you see these massive headphones, you might think, oh wow, he must play computer games and must have a Twitch stream or something like that. He must be like a Twitch millionaire. Nope, not at all. Whenever I was a kid, I always wanted really over the top large headphones and I didn't get them. But guess what? Now I'm an adult and now I got them. So I'm really happy about that. Intermolecular forces, however, are what we're here to talk about. Now, one of the things that we definitely need to know about when it comes to intermolecular forces is polarity. So, one thing that I want to give you a little bit of a heads up about is electronegativity. We had electronegativity on our last test. And electronegativity is very important for defining a compound as being polar or nonpolar. If you remember a polar molecule, or one example of a polar molecule is water. Water, or H2O, is a polar compound, is a polar molecule. And I know that when we talk about electronegativity, it's very easy to talk about, well, um, is this bond polar? But what we want to look at is we want to spend time looking at the polarity of a molecule, not just the bond. And you might think, well, bonds are within a molecule, and if a molecule has a polar bond, well, then it must be a polar molecule. And that's not really the case because you have to then think about the geometry of a molecule. And if you remember last time, and actually, I'm going to ask this to the chat. And here's what I'm going to do. There is a word that I'm looking for. It describes a molecule. And if a molecule is this, the organization of everything, then that molecule is nonpolar. And I'm going to put one bonus point and then we're also going to add it on the last exam. So if the first person, well, yeah, I'm looking for this word. This is a characteristic of a non-polar molecule. And it's a single word. It's something that you maybe learned in like an art class when you were younger. It has to do with where things are. I'll give you a little bit of a hint. Done. Everyone, applause for Kaylee. Hands up, raise the roof, all of these things. If a molecule is symmetrical, then it is a nonpolar molecule. What that means is that if a molecule is symmetrical, then its likelihood of being polar is greater. So we're going to first look at this. Leave the full screen. Here we go. This simulation. No, that's not the one that I'm looking for. Molecule polarity. Let me clear this out. Okay, so let's first start looking at a two-atom compound. So what this is showing us is this is showing basically a molecule that's made up of two different atoms. And if you look down at the bottom, we can adjust the electronegativity. We can make it less electronegative or more electronegative. And these are all just relative scales. If you look how it starts out, what we have is a molecule, atom A and atom B. Atom B is considered to be kind of the mid-range electronegative molecule. Whenever I shift that slider to the right, then we have a molecule that's, well, or an atom that's more electronegative. Now, one thing that we can look at with respect to that is if these two atoms are equally electronegative, how would you describe that compound? Would you say that it's polar or nonpolar? And before we answer that, I want to show you some examples. So let's put both our molecules at being less electronegative. We'll shift molecule or atom A to that mid-range. Notice how there's an arrow and there's basically it's almost like a dagger of sorts. What this is going to show, and I'm going to add this in, is this is going to show partial charges. If atom A is more electronegative, that means it wants electrons more than atom B. Electrons, what is the charge? Add this to the chat, somebody. What's the charge of an electron?
Okay, that's a great question, and it is in our FAQ, so bookmark that so you can reference that.
Negative.
But,
absolutely.
All of the data
Our electrons are negatively charged, which means that if you look at this model right here, I'm going to add this surface. If you look at the clicks on the options on the right hand side of the screen, you have this electron density. Okay. What I've got is and this electron density is just kind of shading. The darker it is, the greater the electron density. So what that means is the more electrons are on the left-hand side of this by the more electronegative atom. I'm going to remove that. And now I'm going to toggle atom A and make it more electronegative. What happened to our dagger there? Well, it kind of stretched out. But in addition to that, we have these partial charges. Switch my color there to get better contrast. Atom A, being more electronegative, has what's known as a partial negative charge. And the reason for that is because it has a higher kind of, or higher amount, or a larger amount of electrons. Atom B, on the other hand, has a partial positive charge. So its electrons are a little bit fewer, or its claim to those electrons is lower. Now, how would you describe, add to the chat, would you describe this combination right here? Would you describe this as polar or non-polar?
So you can review there. Yes, please.
Cortisone, perfect, perfect, Corey. Yes, this is a polar molecule because we have, I always like to think about it as we have two poles. We have a negative pole and a positive pole. So this is a polar molecule. Great job. Okay. Now the great thing about this is we can play around with the electronegativity. And so if I shift both of these molecules to being very electronegative, how would you describe this molecule now in terms of polar or non-polar? Non-polar. Great job, Caitlin. It has no kind of high concentration of electron density. So this would be a non-polar molecule because you don't have, and I'm going to click on partial charges. There are no partial charges. Okay, so then let's go on to a 3-atom display. And this is basically a molecule made up of 3 different atoms. And you could almost think about this like water, H2O. When we have water, it looks like this. H or O, H, and H. Okay, so Here's H2O. What does that look like? Well, atoms A and C, we'll put them both as being basically low on their electronegativity. Oxygen, by comparison, well, oxygen has two lone pairs of electrons, which means, excuse me, those electrons are basically right there. Effectively, what that means is that when it comes to partial charges, we'll click this to show our partial charges. Oxygen is partially negative because it's more electronegative and it's got those lone pairs of electrons. So how would you describe this molecule? Polar or nonpolar?
Or, you know, if any kind of issue like that would be important to us, so we can take it back to the developer who can adjust the model and improve it. And
Does it have any
I was
poles?
notified,
Polar. Great job, Caitlin. Yes, it does. It's got a positive or partial positive pole. In fact, it's got two partial positive poles and a partial negative pole. Now, important detail about those poles is they're not directly across from one another, so they kind of don't cancel out. Okay, now last but not least, let's look at some real compounds. So we've looked at these models, these kind of simple models, a two atom and a three atom molecule. Now let's look at some real molecules, which thought that this is working yesterday. I guess I was using it.
you can,
Let's see if this
if you
works.
go to this page, you can do it on any page, but like if you go to this page, if you wanted to select a certain date range or, you know, a filter, you can filter by like your team.
Okay. Real molecules. There we go. So here what we have is HF. Now, HF is a real compound, hydrogen fluoride. What's the most electronegative element on our periodic table?
Then
Fluorine. Perfect. Now, when it comes to the electronegativity differences between these two, well, I'm going to apply those. We've got 2.1 and 4.0. Is this a polar compound or is this a non-polar compound?
it is manager, but it's useful for.
It is polar. Perfect, cortisone. This is absolutely a polar compound because if we apply these partial charges, we'll see that there's a negative 0.43, which you don't need to worry about the numbers specifically there, but it's a negative value and a positive value. Now, what does a polar molecule look like when we apply the electron density? And this is just a nice little map that shows a compound. Oh, look at that. What this is showing is basically, actually, here, let me,
Export it first.
okay, so this right here, this region of the molecule, or no, I'm gonna, let's go ahead and,
Sure that you are not revealing like,
okay, the red square versus the pink square. Okay, I've got a question for you. We know that this is a polar compound. We know that fluorine is more electronegative. We can look at the gradient at the bottom that shows our relative electron negativities. But my question for you is, if I said, hey, shrink yourself down to the atomic level, what I need you to do, or maybe the subatomic level, is I need you to find an electron. Just find a randomly, floating around, flying around electron. And you have two options. You can either go into this pink or magenta square or rectangle, or the red rectangle. Which one are you going to go into where you think that you're more likely to find an electron? The red or the magenta? Red, absolutely. So this is showing the density of electrons. And this isn't so much a density of like calculations, but I always kind of think about it in terms of the probability. If anyone's ever seen like a population density map of like the city of Houston or San Antonio or something like that, you know, during the middle of the day. Where are most people in San Antonio? They're in like downtown San Antonio because that's where lots of businesses are, and that's where there's high-rise buildings where you can basically stack lots of people. So that's what this is trying to display. This is saying basically, where are electrons more likely to be? Well, they're more likely to be on the right-hand side of this molecule by our more electronegative element, fluorine. Now, if we switch this and we say, all right, let's look at a different molecule. Let's look at O2. Is this a polar or a non-polar molecule? And yeah, it shows O1 and O2, but that's just highlighting the different oxygens. Oxygen 1, oxygen 2. They're the same. Okay, we got to vote for polar. We got to vote for non-polar in a private message, and then another vote for non-polar. And you'd be right, this is a non-polar molecule. Now, think about the electronegativities of two oxygens. Well, they both have electronegativities of 3.5. And then another way to look at this is, let's say that we were to draw a line right down the middle. Is this oxygen, is this identical on the left and the right side of the molecule? Absolutely. So this is a symmetrical molecule, and symmetrical molecules we know are going to be nonpolar. Another way to think about this is I always think about a game of tug of war. Each oxygen is participating in this game of tug of war. They are both equally strong. Who's going to win? Well, kind of neither, because they're both equally strong. So whatever force they're both pulling with, they're going to cancel one another out. Okay, now let's go with this. Trifluoromethane. Now this is a molecule that's a little bit tricky to visualize because notice a couple of things, or I want you to notice a couple of things. F2, F3, and F1. What I want you to notice about F1 is that's kind of in the background. F2 is in the foreground, and then F3 is a little bit kind of adjacent in on the right. So F1 is in the background, F2 is in the foreground, F3 to the right, a little bit in the background. Now, let's go back to the polarity of this question, of this molecule. And before we get to that, how would we describe this shape-wise? And using the terms symmetrical or asymmetrical. Would we describe this as symmetrical or asymmetrical? And I'll give you a line and ask you the same thing. Is what's on the top asymmetrical? Perfect. Now, I want to caution you, some people might draw the line right here and be like, oh yeah, if you cut this hydrogen in half, then half hydrogen's over here and half hydrogen's over there. I like your thought process, but that's not really how a compound or a molecule is going to exist. You know, this molecule, it's in constant movement, it's in constant rotation. And so what that means is, well, sometimes your axis might be right there. Sometimes your axis might be right there. Well, if it's, let me clear this out. If this is your axis, well, you've got two atoms on the left and two atoms on the right. You got two fluorines on the left, and then a fluorine and a hydrogen on the right. So that's asymmetrical. Asymmetrical. One way to think about it with a more critical thought is if it's asymmetrical in any or on any axis, then it's an asymmetrical molecule. Okay, so now that we've established that trichloromethane or trifluoromethane is indeed an asymmetrical molecule, is this a polar or a nonpolar molecule? It's absolutely polar. Great job, Caitlin. Now, our last compound is going to be, well, actually, heck, we'll just go with chloroform. Let's just cut to the chase. Is this polar or nonpolar? Another name that you could come up with for this compound is trichloromethane. It's polar. Great job. This is just like that CHF3. It's got four chlorine or three chlorines and one hydrogen. Now, if I substituted this hydrogen for a Cl, is that going to make my molecule polar or non-polar?
Information that's in here.
I'm going to have a carbon and four chlorines surrounding it. Polar or non-polar?
From the prompt that the expert fills out at the beginning and then the lead wrap up. So it has the lead wrap up and all of that, but it doesn't have any of the survey information from the expert about the.
In this case, if I had four chlorines, that would be a non-polar molecule because my molecule would be completely symmetrical. Okay, so understanding and being able to look at something and classify it as polar or non-polar is definitely going to be on this test. And, I'll give you some models like this. That's the great thing about doing our exams on computer. I don't have to worry about like color printing over anything. But being able to process this, and if I gave you that, I actually move that. If I gave you this, well, that would be a good test question. So now, just as a little bit of an idea of what you could study, I would go through each one of these because it seems to me that these will be good places for me to grab a question. And just go through each one of them and be like, okay, is this polar or non-polar? Let's see our electron density. Okay. Anywhere that you see that electron density darker in one particular area and lighter in one or two or three other places, well, then that's going to be a polar molecule. And you can throw those partial charges on there to give yourself a little bit of a calculation there. Okay. Now, being able to classify a compound as polar or non-polar is very important. And one way that it's important is because what we kind of think about and work with a lot in chemistry, we work with solutions. Now, can anyone name a solution? Add it to the chat. I'll start. Blood is a solution. What's another solution? I'll add another one. Food coloring. Perfect. Orange juice. I'm typing it. These are all solutions. Now, if you think about blood, for example, as a solution, well, blood has a lot of stuff dissolved in it, like red blood cells, proteins, sugars. All of these things are dissolved. So if I were to say, okay, our solution is, or let's go with food coloring. The solute would be, for food coloring, the pigment compound. And then the solvent, well, it kind of depends, but chances are the solvent is either going to be water or sometimes it's like ethanol or something like that. Basically, whenever we talk about a solution, what you need to know and be able to identify is what is the solute and what is the solvent. The solvent is the thing that is in greater abundance. So what is there more of? The solute is the thing that gets dissolved. The solvent is what it gets dissolved in. And a solution is the result. There are a number of different types of solutions. If you get if you get a soda or something like that, that soda has a gas dissolved in it. That gas is carbon dioxide. A sugary drink. So if you also, again, if you get a soda, well, that sugar is dissolved in there. It is a solid dissolved in there. An alcoholic beverage, if you get like a beer or a glass of wine or something like that, well, that's actually That's a number of different things. But one of those things is it is a liquid-liquid mixture. It's a liquid-liquid mixture because it's basically water as the solvent and then ethanol as your solute for an alcoholic beverage. Now, a question of will something go into solution? Will it dissolve? Well, to answer those questions, we can look at a number of different things. A polar solute in a polar solvent will dissolve. A nonpolar solute in a nonpolar solvent. Okay, so I'm going to highlight this. And then I'm going to highlight this. And then an ionic solvent or solute will dissolve in a polar solvent. Okay. However, polar solutes will not dissolve in nonpolar solvents. So what that means is let's take let's take the compound trichloromethane.
Data at this time, but from the work, from the request workload that for black. And then as we get more, as we transition to everyone being in the next level help tool.
Okay. Trichloromethane. What did we say about that compound? Was it polar or nonpolar? If you remember trichloromethane, it was a carbon, and then it has a hydrogen, and then Cl3. Was trichloromethane polar or nonpolar?
Oh, the training is like, it's stuck in the middle there. Here, I'll post it again.
Absolutely. It was a polar compound. You're absolutely right, everyone. Great job. Great job. Okay, my question for you is, will trichloromethane dissolve in water? Will it dissolve in water? Water? Well, we got an okay, so trichloromethane is polar. Water. Is that P or NP?
I posted all those links too in the. Oh, yeah, no worries. Yeah.
Water is polar. Okay. So my question is, will trichloromethane dissolve in water? Essentially, will a polar solute dissolve in a polar solvent? Absolutely. Now, my next question, hexane. Hexane is a compound that is C6 or cyclohexane. Well, actually, no, we'll change this. Benzene is a molecule that is a nonpolar molecule. My question for you is, will trichloromethane dissolve in benzene, a nonpolar solvent?
Whatever is up here in the chart is reflected down here in the corresponding data point. So, you can see what specific questions they are asking, and then you gotta scroll down and don't.
No, it won't. You're absolutely right. So basically, polar loves polar. Nonpolar loves nonpolar. Polar does not like nonpolar, so they won't mix. And that you could kind of phrase as like dissolves like. These two things, if they're the same, they mix well together. Now, the last one is an ionic solute. Will that dissolve in a nonpolar solvent? Well, think about an ion or an ionic compound is just, I'm just going to phrase it as ultrapolar. So it's gone beyond polar to now you just have two separate ions. So an ionic solute will dissolve in a polar solvent, but not in a non-polar solvent because of the fact that if something is ionic, it's basically extreme polar. Clear all my drawings. Got some questions. A polar solute will best dissolve in, I'm giving you a minute on this one, but we're good. I'm pretty sure everyone's going to get this. And if we get 100% correct on this one, bonus point on the last exam. We've already got one out there, so everyone's already going to get 1 point added to the last exam. But if we get 100% correct on this one, then we're going to get a bonus point on the last exam. We got 28 seconds left. Okay, what do we got? We got 29 answers. Okay, don't worry about it. Just answer the questions, the assigned questions. Okay, so what do we got? 27. We're so close. Don't worry, there's more tries. But you're absolutely right. A polar solute will best dissolve in a polar solvent. Okay, next up. Got another question here. Water is polar or non-polar? 1 point on the line. One bonus point on the line. If we get 100% correct, then one bonus point on the last exam.
No, these are sorted by the AI technology.
Okay, 24 seconds left.
Yep. No. Right, we do have a filter up here.
10 seconds.
And so you could filter by product support.
4,
And
3,
then see what
2,
happens there.
1.
So there you see, yeah, for the.
Okay, I think we got it.
Much, the bigger break here, but.
We did it. We did it. We did it. Polar is the correct answer. Water is a polar compound. Okay, so one bonus point.
And then within.
Excellent. Great job, everyone. Fantastic. Okay, got a couple more questions. Yes, you did. You didn't. Okay, okay. I want you guys to get these points. Okay? We're on the same team, pushing in the same direction. We're going to get this. Okay. We've got, I think, 2 more questions. Yes. 2 more questions. Which of the following substances is polar?
So then, yeah, it's.
And I'm going to go ahead and straight from the jump, put 15 more seconds on. And this is going to be, yeah, this is going to be worth a, worth another bonus point.
These are, okay, so the corresponding data points is all of your.
So go ahead and take a minute and try drawing these out.
Yeah, it's what you filtered. So once you filter it, it changes the charts and it changes this data down here, and you can export it. You know, you could download it as a spreadsheet and then open it and manipulate it.
30 seconds left.
That way, or you could just look down here and see, you know.
We got 22 answers.
File.
Pretty confident that we can get up to at least 30 answers. Absolutely, Kevin.
Yeah.
4, 3, 2, 1, 0. Okay, 100% on the line. Close. Okay, what we're going to do, it's Wednesday. I'm going to throw another bonus point. That was a pretty strong showing. So we got 3 bonus points that are going to be added to your last exam grade. Now, what I want you to do is follow along with me for a second. We're going to look at these 3 different compounds. In order to answer this question, what we need to do is be able to draw these molecules. We need to draw the Lewis structure. So what I'm going to do is I'm going to start out with CCl4. Okay. Now, what I want you to notice about carbon is carbon's rolling in with 4 valence electrons. And that, yes, that's on the periodic table, but I think that that is going to save you a step. If you have kind of in your head that carbon has 4 valence electrons, that's going to set you in the right direction. So I would keep that in mind. So CCl4 is going to look like this. Okay. Now that carbon has 4 valence electrons, and it's going to share an electron with chlorine because chlorine's rolling in with 7 valence electrons. Now we don't really need to even draw the atoms of our chlorine because what we can do is kind of look at our molecule like this. And yeah, we can't split an atom of chlorine, but if we look at it on this axis or this axis or this axis, what you're going to notice is that you've got, well, 2 Cl's on each side. And so that means that this is a symmetrical molecule. Now, the next thing that I'm going to do is I'm going to go to CH4. This is going to look like this. See, carbon's rolling in with 4 valence electrons. H, 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 and H. What's our axis? That could be an axis. You got 2 hydrogens on each side. If you want to draw it like that, that's an axis. They're identical on each side. So this is symmetrical as well. Symmetrical. Therefore, it is non-polar. I'm going to draw an arrow. There we go. Non-polar. C2H6. What does that look like? Well, this is a little bit trickier. C, because each carbon is bringing in a total of 4 valence electrons.
Yeah.
Now this molecule, heck, let's split it right down there. It's CH3 on each side, so it's identical. If you split it this way, that's not a really well-drawn straight line, but effectively you have the same number and the same identity of atoms on each side. Now NH3, this is a little bit of a curveball, and I think that it's a good test-taking strategy. Whenever you see a question where it's like, something about this is odd, that's whenever I'm going to kind of judge a book by its cover and be like, that question's odd, or that answer option is odd. Maybe that's a good indication that it's wrong. I'm not going to immediately be like, well, that doesn't contain carbon, therefore this. But I am going to be like, what's going on with that? Now, NH3, if we were to draw NH3, here's what it looks like. Or here's nitrogen. Nitrogen likes to make 3 bonds, and it rolls in with 5 valence electrons. It's going to have that lone pair of electrons. Now, what that means is we're going to have H, H, and H. So nitrogen, hydrogen, nitrogen, hydrogen. Okay. Now, on one hand, you might look at it and say, oh, well, it's got hydrogens on each side, but it's an odd number of hydrogens on each side. So if this is my axis, I've got 1 hydrogen on the left, 2 on the right. If this is my axis, I've got 2 on the left, 1 on my right. If this is my axis, I've got a lone pair of electrons split into 2, half a hydrogen, 1 hydrogen. This is going to be a molecule which is asymmetrical. Asymmetrical, and therefore this is a polar compound. Okay. Now to put this in the frame of what we've been talking about, something being polar or nonpolar, all three of these compounds, B, C, and D, are nonpolar.
Yeah, because I was saying, oh,
Will any of them dissolve well in NH3? No, none of those will dissolve in NH3 because NH3 is polar and CH4, C2H6, and CCl4 are all nonpolar compounds. So those are bad candidates to dissolve um, in NH3. And then here we go. I think this is our last of our questions. No bonus points associated with this one. We got 3 bonus points on the day. That's good. Which of these 4 substances, yeah, will dissolve best in water? Spoiler alert, there's only one. That's correct. I'm not going to add the 15 seconds because I think you guys are going to knock this one out easy.
yeah, that's fine. Yeah. Yeah, yeah, sure.
Mason, that's not today. It never hurts to ask, but not today. What's kind of coded in there is that maybe another day, but not today.
Yeah, you need an invitation to the data lake to see what.
Yeah, we'll do at some point this semester, we'll do a 5 bonus points question. Okay. What do we get? 75%, pretty strong showing. CH4, CCl4, we saw those on the previous slide. Those would not dissolve well in NH3. C6H6 is a little bit of a curveball because we haven't talked about that one yet. But you can look at that and be like, well, that's a carbon and hydrogen containing compound. Chances are that's going to be nonpolar, which is an important thing to keep in mind. If something's a bunch of carbons and hydrogens, it's going to be nonpolar, or it's more than likely nonpolar. Okay. That was the end of our questions. Now, the next thing that we're going to get into when we talk about solutions and what's important to understand with solutions is basically how that solution kind of is made. And so when we look at, is it here or is it here? No, it's not molecule polarity. Simulation. Okay. Everyone sees that share. Yeah, good. When you make a solution, that's not what I wanted. FET, sugar and salt solutions. Link open. Good. It took me saying link open for it to actually open. So sugar and salt solutions. Now, if we were to make a solution of salt water, we would get, some table salt and we'd add it to water and boom, we've got a salt solution. And if you look on the right-hand side, we have a measure of what's known as concentration. So this is basically a measure of how much salt is dissolved in that water. And I'm going to shake it like a salt shaker, shake it like a salt shaker, shake it like a salt shaker, and the salt level is going up. Now, when you have an ionic solution, which is what you would make from salt dissolving in a polar solvent like water, is you can actually conduct electricity with that. So I'm going to do a conductivity test. I'm going to take this light apparatus and basically I'm going to ask, will the electric current that's running from the battery right here, to my solution, make it through the solution to light up my light? And the answer is when you have a bunch of salt dissolved in there, the answer is yes. Now, what about when I remove the salt? Lo and behold, that electric current does not travel through there. Okay, that's because sodium chloride is an ionic solution or an ionic solvent, solute dissolved in a polar solution. Now, if I add sugar, I'm going to continue adding sugar, more and more sugar. Um, my concentration bar for sugar doesn't seem to be increasing. Oh, there we go. Okay. Sugar isn't really changing it. It's not pushing the needle. And that's not causing my light to illuminate. If I switch this over to the micro level, what's happening that makes this kind of illuminate? Well, I'm going to take my sugar and I'm going to clear all my check marks off of there. Adding sucrose, which is an example of a sugar. What's going to happen to that sucrose? Is it going to dissolve? Yes, it will dissolve. And each one of those sugar molecules will float around. But they're not going to stick together because they are soluble, so they will dissolve, but they're not going to be able to conduct any sort, or they wouldn't be able to conduct any sort of electricity. Now I'm going to remove my sugar and replace it with sodium chloride. Okay, there's sodium chloride. What happens? Booyah! NaCl separates, it dissociates into individual ions in a polar solution like water, or a polar solvent like water. So I'll add more. And that's effectively what's happening at the microscopic level. At the macro level, well, at the macro level, we're seeing salt. And even though there's already sugar in here, as soon as I add salt, then all of a sudden, the light begins to turn on because salt can conduct electricity. Okay, well, that's where I wanted to stop today's lecture. I'm going to stop my recording and